All right, let's get started. Today we are going to talk about approximate query processing. And generally, if we have a lot of data, then at some point we will come to a point where we cannot process all of the data entirely anymore. And in that case, it becomes important to select a subset of the data and get some approximation of the query result based on that. Now, the papers that you see here propose methods for doing that. We're going to discuss all of them, some of them in more detail than others. And you can see here that approximate query processing is already an older topic in data processing because the first papers here are already from the 90s. So this is something that people have been thinking a lot about because it is very important once data becomes too large to process it entirely. So in general, here we are dealing with scenarios where processing our entire data is too expensive. So instead of doing that, we rather want to work with a subset of the data in order to get some approximate results faster. And the focus of that work is typically queries with aggregates, like the one that you see here. For instance, if you have done some kind of survey, you might want to find out what is the average salary, for instance, of the people who have participated in that survey. And if I am seeking for that average salary, then often it might not even be necessary to know the precise amount in cents. Basically, it would be good enough to get some ballpark numbers, and approximate processing tries to give you those ballpark numbers, but very cheaply. So typically, we try to reduce the amount of data that we are processing in order to get so-called confidence intervals. And that essentially means that we say that the true value is within a certain interval with a certain probability. So we could say something for the query before, such as that the average salary is in a certain bounds, within certain bounds, with a certain probability. And as we will see later, there are statistical formulas that allow you to get those confidence intervals based on a sample from the data. Now, some of the questions this raises is, first of all, how much should we sample for a given query? And there's different possibilities to bound that. Maybe we have some kind of time constraint, or we have some kind of error constraint on the, for instance, on the size of this confidence interval. Maybe we want it to be narrow enough. Or maybe we just wait for user feedback. At some point, the user loses patience and stops query processing. Also, the question is, when should we do the sampling? Should we try to collect samples at runtime? Or should we maybe try to already prepare samples before runtime that will be used for queries at runtime? So there's different possibilities how to do approximate processing precisely. And in the following, we're going to see two different ways of doing approximate processing. One is called online approximation, and that has already been around in the 90s. The other one is a more recent approach in the BlinkDB system. And we will see that those two approaches, they make different decisions with regards to those questions that we have seen on the last slide. We will start discussing about online approximation. What you see here is the interface for online aggregation. And as you see here, there is a couple of intermediate results being shown. Currently here, we are processing a group by query with some aggregates that we want to approximate. You also see a couple of buttons here, which probably allow you to interact with the system in some way while it is approximating. Does anyone have an intuition about the semantics of any of those fields or of any of those buttons that you see in this interface here? I believe that it is quite intuitive, so I really wanted to see whether somebody maybe can just guess what at least some of those controls mean without even discussing them beforehand. So if anyone has an idea about what any of those fields mean or any of those buttons do, then please write something in the chat. Okay, and there's some propositions. Let's see. Okay, that is a great question. The skip factor, what that one is related to. That is actually a great point. It could totally be like the number of data points that we are skipping over in order to consider only the remaining ones. Yeah, that would totally make sense based on the interface. The semantics is, it's kind of the same. It's kind of the same thing. It's basically how often the the visualization will be updated. Whenever one new result tuple appears, or maybe only every 100 result tuples or 250 result tuples. So yes, in a way, it governs like how many result tuples we skip before we update the visualization. Yes. Mm-hmm. Okay, very good. We have, okay. Probably it's reporting the running average and current 95% confidence interval as it processes. Yes, very good, exactly. So we have a confidence column, which gives us the probability that the true average is within the current confidence interval, and that is fixed at 95%, it seems. And then we have the interval column, which probably gives us the width of the confidence interval currently. And we have the average, which is probably the middle point of the current confidence interval. Yeah. And then we have, okay, and here we have the suggestion that the red button might cancel that query. So I see actually multiple red buttons here. Why do we have multiple red buttons and not only one? And remember that it is a group by query. So we're calculating averages for groups of rows. Anyone has any propositions? We'll have a speed column. Is the major column. Very good, very good. Yes, and here there's the right idea here. Exactly. So what you see here in different rows is the results for different groups, right? And probably this a major column that could be the column according to which we group the rows. And since we have the separate stop button and speed button for each of those groups, probably we can stop calculation for one group if the confidence interval is sufficiently small. And perhaps we can speed up or slow down the calculations for other groups. Yes, very good. And then we finally have this cancel all button at the bottom, and that one essentially terminates query processing for all of the groups. Okay, very good. I think we covered pretty much everything. So here we have the result of a group by query. And as we are watching this result, it would get refined continuously. So the value for those confidence intervals would keep shrinking. And I, as a user, have some influence on how the approximation prioritizes. It can tell the system that certain groups are more important for me than others. Perhaps for some groups, here, for instance, for the second row, I have a pretty small confidence interval. So I could say that maybe I have seen enough. I know pretty well what the average looks like. Let's want to focus on refining the approximation for the other groups, right? So this is continuously refining the approximation, and it is giving me as a user some choice in what is prioritized when refining the approximation. So that is online aggregation. Here you find a summary of the different possibilities for interaction, which we have just discussed. And in the following, we're gonna discuss a little bit about how we can achieve that in the background. Now, let's first of all talk a little bit about how we can calculate those confidence intervals. We start with relatively simple queries. Let's say that we just calculate an average over one column, and we don't have any predicates, we don't have any group by, we just have a very simple aggregation query. Conceptually, what we do here is the following. We introduce a random variable, let's call it R, which essentially represents the grade of a random student. So here we are calculating the average of the grades. And if we have introduced this random variable, which represents the grade of one uniformly randomly selected student from that table, then the expected value of that variable corresponds exactly to the query result that I'm looking for. And I can get some sample from that random variable by simply randomly selecting rows from the student table and looking at the grade. And from that sample, I can derive some insights about the expected value, about the interval within which the expected value is probably located. I can use multiple equations here. For instance, in the paper from the reading list, they propose the Höfting inequality, which you see here, and I won't discuss that in too much detail, but just on a high level, what you see here, we have a probability on the left-hand side, which bounds the probability that the absolute distance between two terms is smaller or equal to epsilon. And here, EV, that is the expected value, and EA, that is the empirical average. So based on the average from the sample that I have obtained, I want to bound the distance between that average from the sample and the true expected value at the same time, the query result that I'm looking for. And the probability that this distance is smaller than epsilon or equal to epsilon is greater or equal to the term that you see on the right-hand side. Here, n is the number of samples that we have taken. UB and LB are upper and lower bounds on the value domain of the random variable that I'm analyzing. So this is one possible formula that I can use in order to reason about the confidence intervals based on a sample from the data that I have looked at. Is there any questions on this? All right, good. So in that case, we're gonna make things a little bit more complex and consider queries with additional predicates here, and equality predicates. Maybe I want to calculate an average for students who follow one specific program. So here we are essentially restricting our scope to those rows which satisfy the predicate. So I can still introduce a random variable representing the grade of a random student, just that here I want to restrict my scope to those students satisfying the predicate in the where clause. Now, if I have restricted my scope, I can calculate confidence intervals using the same formulas as in the previous slide. I just need to make sure that I don't get a sample of general students, but I get a sample specifically of those students who are following the program that I'm restricting myself to. All right. Now, let's look at queries with a group by statement. Maybe I'm not interested in one specific program, but I just want to calculate a breakdown for all the programs. In this case, I conceptually introduce one random variable for each of those groups, representing the average grade for that specific group. And then I can calculate confidence intervals using the method that I have shown before, but for each group separately, using a sample that belongs to the corresponding group. So here I want to divide my entire sample into subsets that are associated with specific groups, and then I calculate a confidence interval for each of those groups based on that subset. So this is how we can calculate confidence intervals conceptually. But how can we do this efficiently in practice? Now, if we start by considering only data access to single tables, we are not yet discussing joins, that comes later, but let's for the moment just think about how we can access one single table efficiently. Now, in general, I can either scan the table or can use an index in order to retrieve a subset of that table. For instance, I can use the index to retrieve rows satisfying certain predicates. I can also use the index in order to retrieve rows that belong into certain groups. Both is possible, and then which one I want to use depends on the selectivity again. There's one constraint, however, because all of those formulas that we have seen before, they assume that I'm analyzing some random sample where the different points in that sample have been selected independently. And that means we cannot use any access methods which retrieve the data, for instance, in a specific sort order. I have to make sure that I retrieve a representative random sample from my data. So here we have multiple possibilities. We can either just scan the data in the order in which it is on disk. We can specifically scan the data in the order in which it appears in some index data structure. Or we can use a sampling based on an index. You could, for instance, use the index on the student program column, and then we could sample from the entries that are associated with one specific program of study. And then I would get some sample from the corresponding subpopulation. Now, those access methods are admissible under the condition that they produce the data in a random order. Does anyone have some ideas about what restrictions apply in those different cases? For instance, if scanning data, what do I need in order to make this admissible? Okay, very good. Yes, exactly. So for instance, for the index scan, that is admissible as long as the index doesn't refer to the column or which I want to aggregate. Because as you can imagine, since the index retrieves the values in sorted order, at least if you have a tree index, then it means that we would start with very low values, and it would take a long time until we come to the higher values. That means that your confidence interval is probably not representative, because one of the underlying assumptions, which is that we receive data in random order, has been violated. Okay, very good. And for the other methods, there's similar restrictions. I mean, for scans, I can apply them as long as the data has not been sorted by the columns over which I'm aggregating. Sampling from indexes, that should be fine since I'm sampling anyway. For the index scan, I might still be able to use it, but the index has to refer to a different column than the one that I am aggregating over. All right, very good. So those are the possible access methods. If I have a given query, then I would typically first decide which of those access methods are admissible using a query analysis. And then I would estimate the cost for specific methods based on data statistics. For instance, if I have a selective predicate in my where clause, then I would probably consider sampling from an index. On the other side, if the predicate in a where clause is not very selective, meaning nearly all of the rows satisfy the predicate, or if I don't have any predicate in the where clause altogether, then I will just scan the data, assuming that it is not ordered. So if we make the list of all possible access methods, then we can choose the cheapest one using methods as the ones in query optimization that we have seen previously. One technique specifically for group by queries is index striding. If you imagine, if you have a group by query, then one thing you could always do is just scan the data in the order in which you have it. And then you could hope that maybe you find about an equal share of members for each of the groups in the query. So all of the groups are updated quite frequently. The problem is if there's one group that is particularly common in your data, and maybe another group that is particularly rare in your data, because that means it will take a long time until you have some reasonable estimate for the group that appears not very frequently in your data. And one technique that helps against that is index striding, which requires that you have an index on the group by a column. Because now you can first of all use the index in order to find out about all the different values in the group by column. And in the next step, you can use the index in order to specifically retrieve values for each of those possible values in the group by column. And in that case, you gain a lot of flexibility. For instance, now you could use a round-robin scheme and alternate between different groups and then use the index in order to retrieve a few sample rows for specifically the current group, and that way you make sure that all the groups are equally updated. Or we have seen that users have some influence in order to decide that specific groups are maybe more important than others. They can influence the speed with those little buttons that we have seen in the interface. And if the user does that, then we can easily take that into account. In index striding, we can just take more samples from the groups that the user wants to get a better approximation of very quickly. So we can take into account user-defined weights when cycling through different groups. Now we have discussed about accessing single tables. Let's see what we can do for join algorithms. Does anyone have an intuition about which join algorithms might be suitable in this scenario and why? If you think back to the standard join algorithms that we have used, is there maybe some algorithms that are better suited for this scenario than others? And what are the things that we want from our join algorithms to make them usable in this current scenario? Some of the join algorithms that we have seen would be hash joins, sort merge joins, block nested loop joins. Okay, there's a vote for index nested loop joins. Okay, interesting. Why do you think this join is particularly well suited? Mhm, mhm. Okay, yeah, that is a good point. And yes, absolutely. I mean, it is well suited because we have one indexed relation. And can anyone generalize from that? I mean, what is the general things that we want from our join algorithms in order to be suitable for online aggregation? Can anyone characterize the ideal join algorithm for this scenario? I mean, typically in standard processing, a join algorithm is good if it finishes the join fast. That is our standard criteria. Does that change in any way in the specific scenario? Okay, so in general, okay, very good clarification question. So yes, this scenario, that was not very specific, admittedly. So in general, in online aggregation, so if you want to use the join for the back end of the interface that we have seen, which continuously updates the query results. If there's a query plan, so the join might even be followed by a different join, but in each case, the join appears in the query plan that processes the query whose results get continuously updated in the interface. I mean, do we care that much about the entire processing time of the join compared to the standard scenario? If you think about a join algorithm that does some heavy pre-processing, but then it is very fast, and in total it's very fast. Is that a good join algorithm to use? Right, yes, exactly, yes. So if we would have any pre-processing, then that would probably require scanning all of the data, and that could be quite expensive. And the whole goal of online aggregation is that we get some approximate values very quickly. But if your join needs a lot of time before it even gets started producing any results, then the whole purpose of online aggregation wouldn't be satisfied, because you would have to wait for that join to finish its expensive pre-processing before you can get any result tuples. And that makes certain join algorithms more preferable than others. For instance, if you think about our standard join algorithms, the sort merge join first needs to sort the data, and that is bad because that takes a little while. So I would not get any updates in my online aggregation interface until the sorting has happened. Similar for the hash join. The hash join, while in total it's great, but before it can get started, it also first needs to build a hash table over one of the over the input relations, depending on which variant it is. And that also takes some time. There might be exceptions if maybe tables are particularly small, but typically it can take some time. So I probably don't want to use the hash join either. On the other side, the nested loop join, and we had that proposition at the very beginning, so that was correct. The nested loop join doesn't need to do any pre-processing. You can start generating tuples nearly immediately, in particular if the inner relation is indexed, and that was also in that first proposition here, then the join might actually be a good choice. Okay, and this is a great point here. one of your colleagues is pointing out that a nested loop join might give us a skewed data because it finds all the output tuples for one page or one block of the outer table at a time. And that is an absolutely great point. I agree with that. So if there is some kind of a correlation that basically the data that you're getting, basically the aggregation column value depends mostly on the value in the outer join relation. In that case, it would take a long time until you get a representative result, because you always take specific tuples from the outer relation and you join them with all tuples from the inner relation. That is a great point. That is exactly one of the reasons why people have proposed specialized join algorithms for this specific scenario. So this is perfect transition to the next point. Wanted to present quickly one specialized join algorithm for online aggregation. And one motivation for that join algorithm is exactly the one that was pointed out here. We want to quickly get representative result data. Also in terms of efficiency, I mean, we have seen that we can use the nested loop join variants, but if there's no index available in particular, then they are not that efficient. I could use a page nested loop join, but then as we know, processing will be relatively slow in general. On the other side, I could use a block nested loop join, but then I would have to spend some time to read the entire block in the outer relation already. And during that time, I cannot produce any result tuples yet. So there's also a little bit of overhead at the beginning until I can finally produce a result tuples. So people have come up with the so-called ripple join, which kind of at least partially overcomes some of those drawbacks. And the way it does that is by essentially alternating between reading data from both of the input relations. The nested loop variants always read some part of the outer relation and then the entire inner relation. So it's somewhat imbalanced. And the ripple join does things differently. It essentially reads a few tuples or pages from one relation, then a few pages from the other relation. Then it joins all the tuples that it currently has in main memory, and it keeps the current tuples in main memory. And then it adds more pages from the first input, and then it adds more pages from the second input, and again produces all, all result tuples that can be produced using the input tuples that are currently in main memory. So instead of squeezing as much as possible from one relation into main memory and then reading the other one, here we are reading a little bit from both relations. We're doing the join and we're reading a bit more. We're doing the join of everything that we have so far. And with that principle, we can quite quickly generate first the result tuples, while at the same time, the overall efficiency is not too bad. And we have a lot of flexibility about how many pages we want to read from both of those input relations. So let's make it a little bit more concrete. The description was a little bit abstract. So here we have an illustration of a ripple join between tables R and S. And here the plane essentially represents the part of the result that we have currently generated. So at the beginning, we haven't generated any result yet, but the ripple join would first of all read, let's say, one page from R and one page from S. And now, after it has loaded those 2 pages into main memory, it can check all pairs of tuples from them in order to verify whether any of them satisfy the join condition. So very quickly, we can produce some first results. Now we keep those input pages in main memory and read another page from R and one from S. So now we have 2 pages from each relation in main memory. We can do the join between all of those tuples and have again generated a higher part of the query result. We read the third page from R and the third page from S, and now we have the possibility to generate all result tuples that can be formed with the first 3 pages from R and the first 3 pages from S, and so on. So this is how the ripple join works. It alternates between reading inputs from both tables and thereby very quickly generates a result tuples compared to the standard join algorithm. So this is a join operator that is optimized for online aggregation. All right, so this was online approximation. Is there currently any questions about that before we switch to the next topic? All right, so now we are going to see a little bit. Okay, that's a great question. What do we do when we run out of main memory? So actually, one of the assumptions of online aggregation is that probably the user will stop processing much earlier before than it takes to generate the full query result. So here basically, if we would do processing long enough to run out of a main memory, and then we would have to shift the things back to hard disk and load the same data multiple times into main memory. So once that happens, then maybe this algorithm wasn't the best choice. So if the user wants a really precise result, then maybe we should have just gone with the standard join operators from the start. But yes, so this is essentially optimized for the case that the user just wants to run this for a little bit, probably before we even run out of main memory. And then the user has seen enough and can already stop processing. But that is a great question. Yes, if we would run this long enough, then this algorithm would probably not our best choice. So this is optimized for running just for a relatively short period until the user stops processing. Any other questions? All right, good. So now we are discussing about a more recent system for approximate processing, which is called BlinkDB. It appeared a couple of years ago, and it essentially has the following interface. Users can specify SQL queries, and together with the query itself, they specify some kind of bounds. There can be either bounds on the error. So here, for instance, in the first query, we want to calculate the average grade from the students, but here we specify that the error should be within 10% at a confidence of 95%. So here we are essentially specifying the properties that the confidence interval must have for the system to stop processing. For the second query, we have specified a different constraint for the same query. We specify that the system should finish within 5 seconds. And here the semantics is basically, give me the best approximation you can, as long as it doesn't take more than 5 seconds. So here the system always tries to come up with the best possible approximation under the given constraints. And in the following, we're going to discuss a little bit about how we can achieve that. One difference to the previous system is that here the samples are not taken at runtime, but we are generating them offline before the actual processing starts. And that means that we have to be smart about selecting the most useful samples. At runtime, we might have a choice between multiple samples for answering a given query. And so we want to analyze the query in order to optimize our selection of samples. And then finally, we process the input query, but not on the entire data set, but only on the selected samples. And that gives us an approximation that hopefully satisfies those constraints imposed by the user. Now, the question is, how should we create those samples before runtime? if we create those samples uniformly, we might miss rare groups completely, because if one group only appears in a few rows, but we have a large data set, then taking a uniform sample will probably miss all of those rows together. So this is why here we are using something called a stratified sampling, which essentially means that we avoid over-representing common groups in the sample. So we essentially cap the frequency at which rows with certain values in certain columns can appear in our sample. And that avoids that we over-represent large groups in our sample, and thereby creates a space to represent the smaller groups. And one decision is which columns I should pay attention to when creating those stratified samples. Another decision is how large the entire sample should be. And typically in BlinkDB, we are creating samples at different granularities. So then at runtime, we can pick the sample that has the right size given specific constraints by the user on runtime or on the error. Our space for storing samples is of course limited, so we have to be smart about picking which samples we want to generate and store. To do that, we use a sample workload, which is meant to be representative for the queries that we will see at runtime. And then when creating those samples, when considering which columns to select for stratified samplings, we prioritize those columns that co-occur in certain queries. For instance, if one query uses those columns in the group by clause or in predicates in the where clause. We can formalize this as an optimization problem. So we essentially say that given constraints on the total available storage that we can use for storing samples, we want to maximize the utility of the generated and stored samples for our sample workload. And once we have formalized that, then we can use existing solver software such as integer programming solvers, which can give me the optimal solution for the corresponding problem. Once we have a query incoming at runtime, then we have to map that query to the right sample in our repository. So we have to decide which sample family to use and which sample resolution to use. The sample family essentially refers to the columns that were considered when creating the stratified sample. So those are the columns where for each value combination, we have a cap on the frequency at which it can appear. And the sample resolution essentially means among those differently sized samples for the same family, which one of them do you want to use for the current query. And in order to decide on the family, we have to look, of course, at the columns that appear in the query in the group by clause and in the where clause. In order to decide on the resolution, we want to consider the user-defined constraints on the processing time or on the maximum error. And then we essentially want to select the maximum resolution, meaning the maximum sample size that we can still process within the time limit, or alternatively, we want to select the minimum sample size that will achieve the error bounds that the user has defined. So either we want to maximize precision under runtime constraints, or we want to minimize runtime under precision constraints. So now we have seen two ways of doing approximation. Admittedly, the second one relatively quickly. And nevertheless, I wanted to ask whether somebody has some insights into how those two methods for approximation compare against each other. I initially said that there is those questions that we ask when doing approximate processing, and that those two methods make quite different choices with regards to those questions. If you compare, for instance, the interface or the processing method, what are the differences between those two methods? If you compare, for instance, the interface. Yes, exactly. The processing method is very different because in one instance, we are generating the samples at runtime. In the other case, we are taking the samples offline before runtime, correct? If you would be the user, which one of them would you prefer to use? If you think about the two different interfaces. Okay, good point. So there's one preference for BlinkDB because the other thing essentially requires you to sit in front of the screen and continuously watch what is happening and then stop once the error bound is sufficiently small. Okay, that's a good argument, yes. BlinkDB is you submit the query and then you can do something else depending on how long processing takes. Online aggregation means that you, in order to exploit all those possibilities for interactivity, you'd have to stay in front of the screen and watch this approximating. Any other opinions on this? Yeah, there's obviously no right and wrong answers here. It's a matter of preferences. And yes, that is a good point. BlinkDB essentially takes all the information it needs from you at one step, and then it just goes ahead with that. Sometimes I guess it might be difficult to specify, for instance, error bounds in advance before knowing the actual data. For instance, maybe if you have a group by query and you want to find out, for instance, which groups have particularly high values, depending on how close together the values from different groups are, you might want a finer, a better precision in order to distinguish those values if they're closer together, while if they are pretty far apart from each other, then even a coarse-grained approximation would already be sufficient in order to decide which groups to focus on for the next processing step, for instance. So some of those constraints might actually depend on the data properties, which you may initially not know. But yes, on the other side, you can specify everything you need at the beginning, and then the system goes ahead with a process. Okay, so yeah, so here we had already some main points. So the way in which the processing works is quite different. On the other side, the interface is also different. One of them specifies everything beforehand. The other one allows you to interact with the system while it's processing, but that might also take more involvement from your side. All right. So in general, approximate query processing is an important topic because if we face a large data set that we cannot process in its entirety because that would be too expensive, then we have to work with a subset of data, and approximate query processing is about doing this in a principled manner. We have seen two complementary approaches for doing that. One of them, online aggregation, already a little bit older. The other one, BlinkDB, quite recent. You make a different trade-offs in terms of processing, in terms of interface. So this was approximate processing. The next time we're going to do a little bit of a summary, and then I'm going to tell you about a couple of topics that we would be discussing in the advanced database systems course next semester, which relate to some more recent research in database systems. All right, have a nice day, and then I see you again on Wednesday.